for the introduction. As Mia explained, I originally come from the theory of history, historical culture. I did some, well, let's say, old-fashioned historical research into the German youth movement and their perceptions of time and temporality. But at one point in time, I thought it would be nice to learn some coding, and that is actually kind of what set me on these kinds of topics. As we discussed yesterday, well, my perspective is that I think that well, coding should be one of the, let's say, tools in the historian's toolbox, at least some basic understanding of how to code. My presentation will not require any coding knowledge or whatever, but what I will do is basically, well, take you through some approaches that I use myself in my own research to show you what machine learning can mean to us, what we can do with it, and also what the limitations are. What I usually do is I understand social media posts as forms of historical representation. So they represent the past in the sense that they are not a copy of the past, but they are, you could say, well, they take the place of things that happened in the past in a certain meaningful context in the present. Now, historical representation in the theory of history, which is also one of my other fields of interest, is usually defined and discussed as, let's say, a constructivist framework with main proponents Frank Ankersmit, Hayden White, for example, who well, say that historical representation is a matter of well, narration. Basically, what historians do is we write stories about the past, and they represent the past. Other than, for example, description or interpretation, representation doesn't suggest that there's some kind of intrinsic meaning in the past itself, but it is, let's say, a mode of meaning making in the present by historians or who else about the past. Now, this perception, I think, well, is quite limiting. It's also modeled on a, let's say, an understanding that historical representation is a matter of professional historiography. So it kind of does no longer connect to the context that we are researching now, social media, because, well, if you take a look at social media, we've been discussing it yesterday extensively. Well, social media, they are interactive, which can raise the question, well, meaning making, is it just a matter of an individual author? But they are also multimodal, so they combine different semiotic modes, so text and audio, video, for example. And it is in the interplay of these different modes that meaning is generated. So this also, well, raises the question whether or not representation or the existing framework of historical representation suffices when we study, well, what we do. So that basically is the, let's say, my theoretical, well, discussion that I'm engaging in. But there are also some empirical issues. Now, when you analyze historical representation on social media, you could ask yourself, well, this narrative approach, does it really suffice? Because it does not necessarily cover multimodality. You could say, well, social media posts, they're micro-narratives, but what if, for example, on Instagram or in memes, for example, the image is more important than the text? So that raises one question. And when you do a qualitative analysis of social media posts, you also always end up facing the issue, well, what exactly does the cases that I selected, what do they actually represent? Do they stand for something bigger? Or, well, should I just focus on the dynamics and not suggest any or make any generalizations about the contents of whatever I chose to analyze? On the other hand, if you want to do a more quantitative approach, you run into all kinds of other issues. One limitation is the availability or absence of metadata. So some platforms, they provide quite extensive metadata, others none at all or very limited. So you're also limited in the possibilities of doing some statistical analysis of social media. And what it also misses if you focus on the metadata only, you kind of miss the representational content. So the semantic and the multimodal context of what is actually represented in the posts that you are analyzing. So that raises the question, well, how do or could we analyze multimodal historical representations at scale? Well, this is where machine learning becomes interesting because contrary to, let's say, traditional statistics, machine learning actually is able to capture semantic relationships in whatever input data you put in. So basically what machine learning does is it trains models that are capable of taking any kind of input data that is basically converted into a numerical representation, and is able to make predictions based on whatever, let's say, semantic relationships between the input data it has learned. So how should we imagine that? Think, for example, of an image. An image has usually got three color. An image consists of pixels, and pixels, they have colors, and these colors are a combination of red, blue, and what else? Red, green, and blue. So you have basically that as input data. Whenever you train a machine learning model, you work with images. You've got basically a matrix of all pixels with 3 dimensions, namely the 3 colors of every pixel. And with text, you can kind of chop up the text in different chunks and attribute let's say a random number to every similar text chunk. So basically you convert text or images into numbers, and machine learning models, they are capable of basically what they do, they compress let's say these matrices of multiple dimensions. And in every moment of compression, and it becomes more and more dense, it learns the different relationships between the input vectors. So they call them neural networks because you could say they're somewhat loosely modeled after how we think. So think of it like this. Whenever we perceive the world around us, we see we have a lot of input data. We see colors, we hear things, we taste stuff, but we are capable of making an abstract understanding of whatever input data we receive. So, for example, if we perceive a dog, whatever color the dog is, we associate it with the abstract concept of dog. So it's a bit similar to how machine learning models work. So if you take a look at the image on the right, so you've got the input data on the left. So let's say a numerical representation of text. It condenses and compresses basically these vectors, these long lists of numbers. It makes them smaller. And in the middle, you've got the latent space, as they call it. And that is basically a very condensed and abstract representation of the input data. So let's say the concept of dog rather than all the dogs that we see around us. Then you've got at the right side the decoder. And basically what that does is it allows for the, let's say, to decode whatever you input into some kind of output function. And that can be, let's say, class labels. If you input an image, you want to know, well, what kind of class is this? Is it a dog or is it a cat or whatever? Or it can do text prediction. So we input the text, but we've masked part of the text. So what should be, which words could fill in the mask? So that basically is how these machine learning models in a very abstract and, let's say, oversimplified way work. What is interesting for us is that this latent space, this very compressed and condensed abstract representation of all the input data that the model is trained on, is able to give a very good representation of the semantic relationships of, well, the whatever input we have. So if we forget in this image the decoding part, so let's say the translation of this abstract representation to something palpable, let's say prediction about sentiments or classes of masked input values, and we just stick to the let's say this abstract latent representation of the input data, we can do all kinds of interesting things with it. Because then when we input a new image into the model that is trained, and usually they're trained on vast amount, millions or even billions of other images or texts. So it knows basically the semantic relationship between all the data that it's trained on. When we input an entirely new image, we can extract, let's say, a vector or vector representation of the position of that image or text in latent space. Well, how should we imagine that? So think of it as a matrix of numbers with multiple dimensions. So 3 dimensions, for example, in the case of these pixels, but latent space can have a multiple number of dimensions. So many that it's impossible for us to imagine or visualize, but we can reduce them to 3 or 2 dimensions. And then you can simply imagine a space, for example, where well, different images or texts are positioned, and well, images that are alike or texts that have similar semantic meanings, they are positioned in that space quite close to each other. So that is an interesting approach that I used quite a lot, and that some of you might already have been using without knowing it necessarily. So what you can then do is calculate the proximity or the distance between these input factors, let's say latent representation of an image of a cat and a representation of an image of a dog, see how close they are. And that gives you a good measure of the semantic relationship between whatever you input. Now, what I want to do is take you through a case that I'm working on currently. I'm analyzing memes from the subreddit history memes, and I use OpenAI's model CLIP. This is an interesting model because it is trained on both images and text, so that the representations in latent space of images and text are, let's say, alike. So the model works like this. On the bottom, if you take, for example, several textual inputs, car, bird, cat, and you decode it to a latent representation, you take an image of a cat, you encode it as well, and then you can basically measure the distance between these vectors, and then you will see, well, that the third one, the cat, is indeed closest to the image. So these are ways of basically using latent representations to classify input data. And in this case, well, we can see it as a cat. Now, this can be used in a heuristical sense. For example, when we work with social media data, you can extract these latent representations from images and text alike, and you can see, for example, or you can use it to kind of heuristically find your way through the data set, or you can use it to cluster texts, let's say tweets, for example, that are very much alike. So let's give you some examples. I used history memes. So what I did is I collected 20,000 memes from this subreddit, the 20,000 most upvoted ones. It was a bit tricky because I actually had to do some OCR to extract the text from these memes, because unlike Instagram, for example, the text in memes is actually embedded in the image. So I had to do some pre-processing. I took out the text, so I converted them to plain text. And I also kind of reconstructed the image without the text, so that it gives a good latent representation. I then used this CLIP model to get these latent vectors. As you see in the right, one example, it's just a huge list of numbers that is basically the coordinates within this latent space. So what can you do with it? I made an example for a multimodal search. What this does is it allows you to input new text or input a new image and search the data set for either proximity to existing text or existing images that are in the data set. So you can go to this URL, and I'll share my browser for a second to show you how it works. So this basically is the interface that you come across. And you can do it text-to-text search. So this means that whatever input text we put in there, it converts the input text to a vector, and it looks at the most let's say the closest other vectors in the data set. So if we try to search for let's say terrorism, and it takes a while. Yeah, so you will see that the results are memes indeed that contain terrorism or let's say semantically related concepts in the text that is on the images. We can also do the same for an image search. So if we input let's say a tank, it will likely deliver memes with tanks in the image. So there we are. Now, this is interesting because you can use it in a heuristic way very efficiently to kind of find your way through a huge data set, in this case, 20,000 memes. I wouldn't even know other ways to kind of do this. Also interesting, you can do an image-to-image search. For example, upload a meme template and well, see if there are any memes that use this template in the data set. Or you can use other images that you want to process. So there you have it. So this is, in heuristic sense, a very, you could say, meaningful way, and you can play around with it. I'll leave it up for a while, to find your way through the data set. So indeed, you can, for example, do some clustering as well, where you find let's say, clusters in the in the data set of memes that are most close to each other. In this case, I clustered on the images, and you can indeed find these kind of meme templates. So you could use this heuristically to do an analysis of meme templates that are used in the data set of history memes. So that is the heuristic part. Now let's take a look at the more analytical part. Because we have vectors of the text, but also of the images, we can also look at the semantic relationship between both. So what I did in this case is I extracted I calculated the similarity, cosine similarity of the images and the texts of every memes internally. So how close is the text on a meme or in a meme to the image of that same meme? And this is the frequency distribution of the results. And what I found is that in machine learning, they use kind of a 0.3 as a rule of thumb for semantic coherence. So what you see is that there's a very weak semantic coherence in the data set, which is interesting analytically, but also shows that we can't just leave it there. We also have to basically go back to the data set and look, well, what's actually in it to make sense of these more statistical findings. So that is, you could say, the hermeneutic circle. So if we look at the content of the memes, then this is the result. So on top, you find the most semantically similar text and images. On the bottom, the least semantically similar ones, and in the middle, the closest to the median. So the ones that appear most frequently. And when you take a look at the contents and you analyze these memes, you see that the most semantically related ones are memes of which the text actually says literally what is in the image. So the top one on the left says, well, Isaac Newton slaps the roof of a car, and you see indeed let's say, a figure representing Newton slapping or attempting to slap a car. So you could say this is kind of a direct representation. The text literally defines what is in the image. When you take a look at the bottom, the least semantically similar ones, there is no relation at all. I mean, in the middle one, you see winged hussars on top of a monkey and Ottomans on top of a girl. Obviously, there is no semantic relationship, at least that I know of, between monkeys and winged hussars. So we can see that something else is happening. What's in fact happening is that memes are primarily drawing historical analogies. That is what you see in these images at the bottom, and to a certain extent also in the ones close to the median. So go back to the the cosine similarity figure, you see that indeed, because the vast majority of these memes have weak semantic coherence, we can conclude that they are primarily drawing historical analogies. And that makes sense because the images, they are viral images drawn from contemporary context. So if you want to do some historical representation using contemporary meme templates, you are basically forced by the medium into drawing historical analogies. So by conclusion, what I think is that machine learning can be very helpful, especially these latent factors, to understand semantic relationship between whatever we input. It can also be just text or just images, but in this case, let's say the multimodal dimension worked well for me. And indeed, spatial proximity distance is a good measure for semantic proximity or distance in the input text. So you can use it both heuristically and analytically, and I think I showed some examples of how you could do that. But for me, I think also the interesting question is, well, what are the implications for this entire exercise for, well, the entire idea and the philosophy of historical representation? Because if these multimodal models or machine learning models in general are capable of learning semantic relationships without any human interference, is it then indeed so that representation is just a matter of attribution of meaning on behalf of the historian? Or could it be indeed that the semantic coherence is already in the sources that we try to read as historians? Some limits, 2 notes, basically to close off. Do be aware that latent space always represents the biases of the input training data. So if you can imagine that, for example, women are more close to kitchens in the input data than men are. And you need some coding skills still, I would say, because you see an increasing number of platforms online that kind of well, allowed to do these kinds of analysis, but very often they're still paid. If you want to learn a bit of coding, I would suggest using Python, because that is the language that is most prominently used by people actually creating these models. And the website that hosts my my example is one to explore as well, because that is, if you look in the spaces section, that is where a lot of, let's say, state-of-the-art machine learning models are disclosed and in interfaces that you can use as well. So it's very valuable to explore. So I'll leave it there. Thank you.